All right, it's 1 o'clock and it's time for our webinar about using the FEM-Design API in C#. My name is Johanna Riad and I'm going to be your host for this webinar. And with me, I've got my colleague, Alexander, who's going to keep track of questions and comments during the webinar. Speaking of questions and comments, please, if you have any questions or feel that you want to add something or have any comments of any kind during the webinar, you can just write it in the panel. The same goes if you have any technical issues with the sound or quality of the video, and we will try to sort it out if possible. Before getting into the webinar, I would just like to introduce myself a little bit. So Johanna, as I said, and I work as an automated workflow specialist at StruSoft, which means that I help our customers make their workflows more efficient and improve the workflows in different ways. And that can be holding a webinar such as this one to educate you in how to get started. But also we do projects for customers where we actually help them create scripts and custom adaptations of our programs that they can use in their business. So if you're interested or curious about that, please feel free to get in contact with us and we can discuss this further and help you how to get started on your automating journey. All right. This webinar is going to be recorded, so you can at any time go back and watch it afterwards, which means that if I'm moving forward quickly, which I may be today because there's a lot of ground to cover, you can always go back and look and you don't have to worry about taking notes frantically as we go through the webinar. All right, I'm going to turn off my webcam when I'm showing you things, but I'll turn it on at the end again. Let's see. All right, so I think you can see my my screen. I'm going to keep the PowerPoint in not full screen mode because I'm going to jump a bit back and forth between it and some other things. So let's see. The agenda for today is, first of all, I want to explain open source a little bit to you. And that is because our FEM-Design API is written in open source, which means that anyone can access it and view the source code. And I think that's very powerful in many ways and useful for you as users to be aware of. Then I want to explain the FEM-Design API and how it's structured in C#. And this webinar, it is going to be a little bit more technical than some of the ones that we've had previously. So we'll go into more of how the code is built up. And I think that is actually really good for you if you want to start coding yourself, to just have some basic knowledge on how it all works. And then we'll have some more practical examples, a couple of demos where I've chosen to show a parametric study of concrete stiffness and also an optimization of a thickness of a slab and required reinforcement. And at the end, I want to show you how you can contribute to the API if you find that interesting. So let's go ahead. So open source, the main idea behind open source is that we get transparency. This means that you as users will not have any black boxes where you can't find out what happens in the code, but you will actually be able to see in a function where you put any input and you get some output, you can also see what the function does if you're interested in that. And I think when I was working as an engineer, I found this really useful. I didn't really trust other people, so I would always want to be able to see what was going on behind the scenes. And I hope you think that's a good thing as well. Then we also have the possibility for you guys to add your own things or adapt the API to suit your uses. So our users are going to use the API in different ways and want different things from it. And this means that you can kind of customize it to work at its best for you. We also think that 2 heads or many heads are better than 1. And by working on an open source project where everyone has the possibility to add and adapt, we think we will get much further, much faster. And that's kind of a win-win situation for everyone. Also, it's more fun doing things together, right? If you're interested in joining this open source project and actually contributing as well as using it, then there are a couple of more advantages. This is a way to showcase your skills within coding. So if you contribute to the API, we will write the credit for the part of the code that you've written, and that will be public for everyone to see. So it's quite nice. And we will also give you some extra first-class support, because if you're doing something and it could benefit others, we will have the possibility to spend some extra time helping you make sure that you succeed, because that will also, as I said, benefit others. If you're just working on your own problem, I mean, we will of course help you as well, but you won't have that like business class experience. And in the end, there's also the quality control aspect. If there are others that see your code, for example, us, and maybe other users, there's a much larger chance that any bugs will be discovered. So keep that in mind as well. Okay, so that is that about open source. Just moving on and taking a step back to what an API actually is. I think those of you who have seen my previous webinars may have seen this picture before. An API is an application programming interface, and it's a way for a user, such as yourself, to communicate with an application, such as FEM-Design, without using the normal user interface, but going through programming instead. So this is illustrated with the user, the restaurant guests, sending a request to the restaurant kitchen through the waiter, and then getting the response, the food, back. And that's like the main idea. I also promised to explain what C# is. And C# is the programming language which FEM-Design API is written in. So it's a modern, object-oriented and type-safe programming language, according to Microsoft. But I think the most important thing to note is that it's a programming language. And if you have any experience with programming from before, maybe you've used Excel or MathCAD or VBA in Excel, or you may have used Python or MATLAB at school, then C# will be easier for you to pick up. So just because it may be another programming language than you've used previously, you will still have a lot of use of your programming skills. And if you're completely new to programming, C# is a good place to start. So yes. Moving on to this schematic of the FEM-Design API. So I just wanted to show you a little bit how the API is built, and illustrated it with this sketch. So you got the FEM-Design application here on the left. I hope you can see my mouse pointer. And you've got an intermediate text format here in the middle, which is basically the information that is in the FEM-Design model, but just in a text format. And then we've got the API, which is based on the text formats. So the API also consists of some different parts. And the one that you need to pay most attention to is the FEM-Design core, which contains all the main functionality of the API. So all of the main functions that we use to manipulate the FEM-Design objects. And then we also have these wrappers, so to speak. So it's the Grasshopper and Dynamo projects, which just create Grasshopper components or Dynamo nodes out of the core functionality. And then we've got the samples, which are samples of what you can do using the core functionality. So this is what's most important. And I think for you also, the samples will be really important to get started, because a good way of starting to code is always to kind of look at an example and then try to change it and adapt it in different ways so that you get familiar with the way it works. Okay, I just thought that we should look at one of these StruXML files quickly, just so that I can show you a little bit more how it's set up. So in FEM-Design, if you have a model, you know, when you go to Save As, you can choose the normal str format, or you can choose the StruXML. So if I go to a StruXML file that I've saved, and I open it in a text editor, I use Notepad++, which I think is quite convenient. Then you can see the way the StruXML file is organized. So you got a database which has different entities. And for example, in this model, which we're going to look at in the demo later, we've got a number of different columns. You can see here, there's a bar with name C1, then C2, C3, C4, etc. And then we've got 4 different walls, which are slabs. And we've got one slab, which is a plate. Then we've also got some loads, we've got some supports, sections, materials, and so on. And what is nice to know about this is that you can also expand these, and you can see all of the different attributes that are relevant to each object. So when you're working with our API, a lot of what you're doing is actually changing the stuff that's in here. I think you don't really need to go into these files and look at it if you're not interested, but it's good to know that it is set up in this way, and sometimes this can give you a clue on what you should write in your C# code. All right. There are a number of different ways that you can download the FEM-Design API to C#, and we will look at the different ways that you can do it. The first option, if you like coding and maybe you want to contribute to the code in the future, and you want to be able to have your own copy of the code, but that is linked to the main code library, then you should do this first option and create a fork, is what it's called. And let me show you how that is done. So the FEM-Design API is stored on a website called github.com. So if you go to this website, github.com, and you search for StruSoft or FEM-Design API, you will find this page. And because I've already been there, I got it in my list. And this is what it will look like. And this is where all of the code is stored. So if you want to create a fork, I can't do that right now because I've already done it before, so I already have my fork. But you can just go to the contents, contributing, and you can go to the contribution guide and click this. And then you will have a step-by-step guide that GitHub created on how you can do that. If you run into any problems with doing this, please get in contact with us and we can help you. Okay. The second way, let me just go back a couple of steps. The second way, if you want to test coding in C#, but you don't really have any plans on contributing in the future, and you don't mind just having a dead copy of the API as it looks right now, without any changes that we make being included in your copy, then you can do this option, which is the quickest, and you can download a zip file. So the way to do that is just, again, go here, and then you press the green button, which says code, and you press download zip. So let's do that. And what you need to do once you've downloaded it is right-click, go to Properties, and you need to check this Unblock button and apply. Press OK, and then you can extract it as usual. So let's extract it there. You should, of course, put it in another folder than the downloads folder, but let's just do this for now. And then you get the whole library available here. So I think I will show you what it actually looks like in when we go to Visual Studio, which is the place that I do my coding. So let me open up. Let's see. I'm going to go to the solution, which I have my own fork in. So I just open that up. So I'm not going to give them feedback right now. All right, so this is, first of all, this is Visual Studio Community, where I do my coding. I can read the code here, I can write the code, and I can run it from here. So this is a program that you will need if you're planning on using the API in C#. And it's a free program that you can just download. So this is the version that I'm using, Microsoft Visual Studio Community 2019. But I'm sure there are later versions that you could use just as well. But just Google downloading this and you will find it. And then when you open the let's see, the SLN file in Visual Studio, you will see this view. And here at the right-hand side, you've got the Solution Explorer, which shows you what is in the FEM-Design API solution. So as I spoke about earlier, we've got the FEM-Design core, right? And then we've got the Dynamo library and the Grasshopper library, and also the samples. Then for our use, we've got some tests as well, which we run before releasing new versions of the API, but you don't really need to think about this too much. So just quickly looking in the core folder, for example, you can see that we got the different bars, we got calculate, we got model, materials, loads, and so on. So you can navigate through this folder and find the different functions. And you can also search for things, so like maybe point support, and you can see where that exists in different places. Okay, let's close that search. And I think the main one for you to start off looking at is the FEM-Design samples. And let's open that. And I just want to explain to you quickly how the samples work. So this is a project which has got the different classes in it. And the most important class to note is the main one, which is here. And this is the function. When I press like play here to run the code, this is the function where it will start running. So what you need to do in order to run the different samples, you need to choose here at the bottom which one that you want to like activate. So in this case, the one called parametric study is activated because that has not got the 2 dashes before it. So that is the one that will start running. But if you, for example, are more interested in running the change length of beams or beam, what you do is just delete these and you put them here instead, and then it will run this one instead. Make sense? Okay. Just touching upon a third way of using the FEM-Design API in C# is if you're perhaps creating your own like larger code project and you don't want to have all the FEM-Design source code visible in your solution, then what you can do is you can reference the library through something called NuGet. And one of the examples that I'm going to show you is done in this way. So I'm just going to show you in a while what that looks like. It's very easy to do. I did it for the first time the other day and it was just, yeah, it was very self-explanatory. But the disadvantage of doing it this way is that you don't have access to viewing all of the different functions. And so it's a little bit harder to write your code because you can't really look at how it's built up. All right. So just before showing you the demos, I want to touch upon when to use what. So I've had webinars previously in FEM-Design API in Grasshopper. And I think that is Grasshopper or Dynamo is actually the easiest way to get started if you've got no experience previously. And if you're doing smaller projects or working on linear problems, which is where you have maybe you have a model and you want to do certain changes to it and then you're finished, Grasshopper or Dynamo is very suitable. But if you prefer coding line by line and have some experience with that from before, maybe C# is just preferable for you, easier to start with. But also if you want to use loops, so if you want to maybe run an analysis and then run it again with some different input options and then run it again. So if you're doing for loops or while loops or anything like that, it is easier to do in C#. And that's also why I've chosen the demo as of a parametric study and an optimization problem. And then if you're doing larger code projects, it's also much easier to work in C# than in Dynamo and Grasshopper. So that's kind of a guideline. Let's see. Okay, so that was the end of the presentation, the general stuff. So let's go into the demos, which I hope you will enjoy. Let's see. All right, so the first demo is a parametric study, and I've written it within the samples folder just as a new sample, which is not live yet, but I'm going to show you at the end of the webinar how we can make it live so that everyone can access it. And let me open the model as well. So let's see where I've got it. A long way to search here. All right, so this is the model that we're going to look at for the parametric study. And I've chosen, as you can see, to make a very simple model, but that is just because I want to be able to show you how it's running live. And if I made something bigger, it would just take too much time to run to show in a short webinar like this one. But so basically, it's a concrete slab, which is supported on 4 concrete walls in the middle, symbolizing maybe a core in a building. And then we've got steel columns around the edges. And the concrete plate is rigidly connected to the walls, and the columns are hinged in both ends. So what I want to do in this example is that I want to test how cracking in this slab could affect the load distribution between column and wall. Because as you know, concrete, when it cracks, it loses some of its stiffness, and then it will go from if it's very stiff, this will kind of work a little bit like a console, and more load will go to the core walls. But if it's very cracked, the stiffness will go down, and we will have a more even load distribution between the core walls and the steel columns. And this is a type of problem that is quite common in structural engineering. I find that you may not know exactly how much you expect the concrete to crack. And it can be interesting to check, okay, so what if it cracks a little bit more than we think it will, or a little bit less? Will that affect the load distribution, or will it just be sort of the same and we don't really have to think too much about it? So I just need to not have this model open when I'm running the code. So I'll just open something new. Let's do that. So the way that I'm going to do this in the parametric study is that I'm going to vary the E modulus on the concrete slab that I showed you and put it to start at 20% of the entire stiffness of the slab and then go up in steps. So 20, 40, 60, 80, and 100% of the stiffness of a completely uncracked slab. And the first thing that I need to do, by the way, of course, these examples will be available for you to look at later. So if this is going a little bit quickly, know that you will be able to look at this on your own computer slowly later. So don't worry, it's completely normal if you don't follow along exactly what I'm doing. But the first thing that I need to do is I need to set the path to the FEM model or FEM-Design StruXML file that I'm going to analyze. And then I'm going to choose a folder which I want to output some modified models to. And I also need something called a BSC path. And let me show you what that is. So I should not have closed that down quite so fast. Let's see. So a BSC file is something that you will need when you want to extract results from your FEM-Design model through the API. And the concept, it's, I think, a little bit confusing. But what you do is you go to this list tables, you choose the model, and then in my case, what I want to do to extract is the results for the point supports, because I know that if I can read the force in the point support, I can read the force in the column, and then I know how the load distribution changes. So then I press load cases. I'm working with load cases in this case. I choose point support groups, ultimate, and I've got my load case that I want to look at. Then I press add to batch, and then I choose save batch. And then I save it as this file, basically. And what that file is going to do is when we're running the code in the API, it's going to tell the program that okay, so the user is interested in extracting the point support reactions as a CSV file. And we'll see how that looks in a minute. So this is something that you need to do before starting to run your code, but you only need to do it like once for every type of reaction that you want to read. And then you've got your BSC file that you can use for any other projects later on. Let's do this. Okay, so this is where we were. So I've got the BSC path. I just set it to the one that I just showed you, the point support reactions.bsc. And then because you should be able to read more than one result type, if you like, you have to create a list of BSC paths that you add the one that's relevant to. And then if you have more, you can just add more of them. So this is what happens in these few lines. And then the next thing that I want to do is read the model from the StruXML path. And I think we're actually going to start the code here. And I'll put a breakpoint. And the breakpoint means that the code will run until it gets to here, and then it will pause. And this is really useful for you to use when you're writing your own code and you kind of want to see what happens in each part of the code. So let's start it. Okay, and now we can see that it hit the breakpoint. And we can also see down here in our locals model that something has happened. And this is also something that's quite useful for you to be aware of. And this is where you can see the different variables that you've defined in your code. You can see what they're assigned to at the moment. So we can see that our StruXML path, the first one that we created, it has actually become the one that I wrote up here. And if I press F10 or step over up here, then I can move the code forward line by line. So I can just follow along in what happens in every step. So now we finished executing this line, and we can see that our model has now become a FEM-Design.model. It was empty before. And what's also good to know is that you can expand this. So let's press that. Let's actually do this so we see a bit more. And now you can see all the different attributes or properties which are within the model. So we can see that we've got model, we've got materials, which I'm curious about right now. And we've got 3 different materials. And we've got the first one, which is called C2530. And then we've got the second one, which is called custom. And this is the one that we're going to change the e-modulus of as we're moving forward in the code. You can't change the e-modulus of the standard library materials. So those are like locked. But if you create your own custom material, you can. But this is just a good thing for you to know that you can look at your different variables here and you can kind of investigate what they look like. Let's see. So I hope that you're following along so far. I think we'll save questions for the end, or if we don't have time, we can get back to you after the webinar. But I'm hoping that you can kind of follow along. So what's going to happen here then is that we're going to read the slab that's relevant, and we're going to read its material and read that material's e-modulus. So let's jump forward a couple of steps. Made this maybe too small. So we can see that the ECM is set to 31,000, which is the standard value for that type of concrete. And then what I'm going to do in this for loop is that I'm going to change the e-modulus. So let's go through the first iteration. So I'm creating a new variable called new ECM, and I'm going to multiplicate the old ECM with 0.2 times I, which is the iteration of the loop we're at the moment. So now we're at the first iteration of the loop, so I equals 1. And then we can see that the new ECM has become 6,200, which is 20% of the beginning value. And then what we need to do is just change the material e-modulus and then save the model is what I'm going to do in this example. And then the next step is to run the analysis. So let's do that. The first 3 lines here are about setting up the analysis, and the last one is actually running it. So let's see what happens. So you see here that the model opens and it's starting to run. And you can also see that the StruXML file that's running is one that's called sample slab out 6,200, which is what I chose to name the different versions of the model after the relevant e-modulus. Then the next step that I need to do is that I need to read the results from the CSV file that's been created. And I want to show you what that looks like. So you see right now, 1335, a new CSV file was created with point support reactions. and it looks like this. And it's got all the point supports, and it's got all the reactions. And this is the way, at the moment, this is the way that you get results in the FEM-Design API. We are working on making a little bit of a smoother process for the users, but this is what you will have to deal with for most of the types of results for now. What I did is I just pretty much Googled how to get data from a CSV file into a C#, and I found this example that I copied and edited a little bit to be able to read the data into C# here. So I'm not going to go into how that is done exactly. You can look at that later for yourself. But if we run the script now, I press continue, so now it's going to run without stop points. Let's see what happens. It's opening the next iteration of the model, which has an E-modulus of 12,400, and it's running that. And what I'm at the same time doing is outputting the support reactions into my console, which is a way I can just show what's going on in the code as it's running. So let's wait until it's finished. It's a couple more iterations. So last one with the full E-modulus. All right, and then it's finished running, so it closes down. Now you can see that you got the support reactions for all of the different models with the different versions of the E-modulus. And you can see that if we look at maybe this S2, which is quite large, it starts off as 89 when we've got a very cracked section. Then it goes down to 87 here, and then it goes down to 85, 84, and 82. So then we can see that the way we set the stiffness for the plate, it will affect the load distributions between the columns and the walls with a few percent at least. So it could be relevant in this case. If you got a taller building, it's definitely going to affect this more. So it could be quite useful to be able to do this check. All right, that's the end of this example. And as I said, this will be available later for you to look at. So then you can look at every line and step by step and kind of go through what happens. Let's look at the next one. So I'm going to close this, close that. And let's go to this one instead. So you remember that I mentioned that there was a third way of using the API. This way, if you want to create your own code library and use FEM-Design API as a reference, you can reference it through NuGet. This is what I've done in this example. So this example will show how that can look. And what I did here is that I created a new project or new solution actually. That is a solution with a console application. I recommend you use console application or forms application if you want to do something new by yourself, because that's quite a lot of the setup that you will need is already done. And then what I did is I went to dependencies and I right-clicked dependencies and pressed manage NuGet packages. And then you can just search for FEM-Design, and you will find this one. And if you don't already have it installed, there will be a button somewhere saying install, and you press that, and it's done. So then you have FEM-Design as a reference. Just to mention, you see that there is a small warning triangle here right now. This is just a something that we need to fix in the setup so that the warning message disappears, but it's not going to create problems for you even when you see it now. So don't worry about that one. So let's go back to the example itself. And then what I do here is that I press using, or I write using FEM-Design as a way of referencing the code into this specific class. And this example, let me show you. Is even simpler than the last one. This is just a slab that's supported on either end, and it's loaded with a uniform load. But what I want to do here is that I want to calculate what slab thickness will give me the cheapest solution. So I've assigned a cost to a concrete, the material concrete, and I've assigned a cost to the reinforcement. And I want to find which thickness of the plate will give me a reinforcement so that the total cost of reinforcement and concrete will be as low as possible. Does that make sense? So I would expect if I have a very, very thin plate, then I will get loads of reinforcement, and reinforcement is quite expensive. So then I will probably get an expensive solution. But then again, if I have a very, very thick concrete plate, I will have so much mass that it will be expensive anyway. So the solution should be somewhere in between very, very thick and very, very thin, I think. So let's not have this open when we're going to run the script. And let's look at the code. So the code in this example is actually, it's very similar to the one that I showed you before. It starts with some BSC paths and a path to the model. And in this case, I'm actually not going to save every iteration of the model. I'm just going to overwrite a model which I choose to call temp.struxml, just to save some space on my computer. And here you can see the stuff that I talked about, the concrete cost and the reinforcement cost, then the concrete weight and the reinforcement weight as well. So let's start it up. All right, so you can see that some of my locals again have changed. When I'm doing this, I'm using FEM-Design's auto calculation module for the reinforcement. And then I have to do some different setup for the analysis that you can look at this in more detail at another time, I think. So let's just move forward to here. I've chosen that the lowest or the thinnest I will allow my slab to be is 200 millimeters, and the thickest is 700. I feel that anything below this or above that is unreasonable, and therefore I choose that as limits. And then what the loop will do is that it will set the thickness of the slab, it will save a temporary model, it will run the analysis, and it will get the concrete weight and the reinforcement weight. And when it runs the analysis here, it doesn't only run the analysis, it runs the design in FEM-Design. and then I calculate the cost, and then I write that to my console application. And then I go ahead and do the same thing for the next thickness of slab and so on. As you may noticed, I've got these functions here, and that is just something that I wanted to show you, that if you want to structure your code a bit differently, you could put functions of things that you use a lot in the same, like in a separate function, and then you can call that function from like the main function. And that means that when you're looking at the main function, you don't have to see all this text like again and again, especially if it's part of the code that you use more than once. It's quite logical to do it in this way. And I think it makes it look cleaner to read up here. So the run analysis function that I created here, it's got all of these different lines that we need to set up the analysis and run it right here. And I could actually have put the analysis setup in there as well. I don't know why I didn't. One thing that I wanted to comment on is this line of code. Maybe I should have done that in the last example because it existed there too. But you see that there is quite a lot of inputs required for this function. So it doesn't really make sense when you look at it like this. But a tip here is that if you erase the parentheses and then you write it again, you will actually get the clue of what all these inputs are. And in my case, the inputs are a stage analysis setup, a combination setup, a frequency setup, a footfall setup, and then we got the booleans for deciding what types of calculations to do. And you know, if you press analyze in FEM-Design, you have to like check the boxes of the different types of calculations that you want to do. This corresponds to that. So in my case, I want to calculate the cases, which is this one. Oops, disappeared. But I'm not interested in calculating combinations or stability or anything like that in this example. So all of the rest of them are false. So it's quite useful to know that you can kind of get hints while you're writing the code. Okay, so let's actually go ahead and run it. So see what happens here. Okay, so it ran the first one and it's starting on the second one. And it's going to output the cost for each iteration here in the console app. So I'm outputting the cost, which is this number. I totally just made up the cost of the reinforcement and concrete, by the way, in this example. So it's not realistic, but just as an example. So the cost and also the thickness of the slab that was used in that iteration. And we will see this move on step by step. So I'm just going to wait for a minute. It is kind of annoying that FEM-Design will like pop up and then close down again when you're doing these kind of analysis. But what I would usually do is I would write my code and then run a couple of iterations to make sure that it seems to be working. And then I will just like go for my coffee or lunch or go home for the day so that you don't have to sit and watch your computer doing this live. It's also not very convenient working on your computer at the same time, partly because it takes a lot of computer power to do this, and partly because, you know, it keeps popping up and down. So maybe you're doing something else and then it will pop up on top. So I think, let's see, I set 0.7, I think, as the thickest. So it should be nearing getting done, but I think perhaps I'm going to stop it anyway. So I can do that by just putting a new stop point. There. Okay, so I stopped it, and I just wanted to show you what would be the next step once it had finished running. What I would do is that I would take the list of costs which I've created while running this. So let's see. Costs. And I will copy them. And I've got so many Excel files open, but let's just take a new one. And I would paste that. And then on my computer, my Excel is in Swedish, so I will need to change the dots to commas. Let's see, for them to be numbers. Replace all. And then I know that this was 0.2, this was 0.25, and so on. Let's see, there and there. And then I can create a, for example, a scatter plot. And in this, I can add a trend line. So let's see. Maybe it's a polynomial. Could that be right? You can kind of, I mean, it depends on what type of problem you're looking at, but you can perhaps find a trend line that suits your problem, and then you can kind of look for the optimal solution at the lowest part here of the trend line. So in my case, it seems to be when the slab is around 400 millimeters thick, that would give me the lowest cost. Okay, so let's stop this and let's close that. And I think that is what I wanted to show you demo-wise, except for the last part, which is how you can then contribute your code to the main API. So imagine that I created these examples, and I felt like they're really good examples that maybe someone else can use and that I want to show off. Then if I had chosen the first way here, which is creating a fork, what I can do is open something called GitHub Desktop. And you can see here that we have something called changes. So this is quite cool. This actually compares the code to the source code, so to speak, and we can see what has changed. So here in change length of beam file, it seems that I just accidentally created an extra line. In the main file, I wrote parametric study and I commented out change length of beam. And then we've got the parametric study, which is a completely new class that didn't exist before. So that's why it has a plus sign over here. And I want to commit this to the main API. So then I just write here that I created a new example of a parametric study or something like that. And I press commit to master. And then I push it. And then what I can do is that I can go to my local fork, which is where the code now exists. And I can create something called a pull request. You don't have to remember all of this. I just wanted to show you so that you know. And if I create a pull request, let's do that now. Create pull request. Please include this in the main API version. And I create a pull request. Then what's happened is that I have sent a request. This is from my private email, I should say, or my private GitHub account. And I've sent a request to the official me and Alexander and Andreas to take a look at what I've done. And if they approve, take it and put it in the main version of the API. So that is how easy it is. If you don't have a fork, what you can do is you can go to issues. So let's go to this one. You remember this one wasn't a fork, it was one where I had just read the FEM-Design DLL as a dependency. What I can do is I can just take this class, which is the one that I want to commit. I can copy the code and I can put it in Notepad, for example, and just save it as optimization.txt. Did I succeed? And then what I can do is I can here create a new issue, and I can write maybe that I have something that you can include in the main API version, and I can write it's an example, an optimization maybe. And I can submit this issue, and then I can go to where did I put it? There. Okay, I don't realize where I actually put this, but I had one that I created before that I have here. And then you can just pull that text file to here. You can comment it, and that will also be a way to give your code to us. All right, I made it with 2 minutes to spare. I hope this hasn't been too intense. This was all that I wanted to show. So
thank you,
let's.
Anna.
Thank you.
Yeah. Great presentation. Do we have time for a single short question, I think?
Yeah, I think so. Maybe one or two.
One or two. Okay, so a friend of us asked if it's possible to do a climate analysis regarding the CO2 of the cost function in the example you showed. So can we have that? Can we optimize the climate, so to say?
Yeah,
so,
that's a very good question, I think, and I'm glad that you asked it because I hope. I think I should have remembered to say something about that myself. So in the example, as you said, I optimized for cost, but it could be anything as long as it's a number. So I could call this variable concrete climate cost, and I could put the CO2 value and call it reinforcement climate cost and put the CO2 value, and I would be able to run the exact same example. So it doesn't really matter what type of cost it is. You can use this example either way.
Great.
Okay. Do we have maybe one more short question, or should we maybe get back to you afterwards? What do you think?
I think I've answered most of the questions in the chat, and a few that needs to be elaborated a bit, I think. But we will get back to the people asking questions in the chat as well. Yeah,
exactly. We have your emails when you signed up for the webinar, so we can just get in touch with you afterwards and make sure that you have answers to your questions. And also, so we should end this because time's up, but also we would love it if you will get in touch with us if you have any questions, comments, or any kind of things that you want to discuss. We're happy to like guide you if you feel like you want to get started with this, and there are plenty of ways we at StruSoft can support you in your journey towards automating your workflows. So don't hesitate. And thank you very much for listening today. It's been fun. All right. Bye-bye.
Thank you.